Hi there, welcome to your lesson on optimization. This is a key application of maximum and minimum points, our most recent lesson. And just like this cute little hedgehog, we are ready to go and live life to the fullest. So let's get started. Let's recap a key point from the last lesson, which is this. If we have a curve, and on that curve we have some maximum and minimum points, we can confirm those are maximum and minimum points by using what we know about derivatives. At a max and a min point, the derivative will have a value of 0. And the reason for that is because the derivative represents the slope, and at a max or min point, there is no slope. So at that point here, which has an x value of 9.69, if you put it in the derivative, you will get a value of 0 because it's telling us right there is a 0, there is no slope. Okay, and then we found out, well, what if you take an x value before 9.69? Any x value back here, any x value. And I took an x value of 5, for example. I put that in the derivative. That produced a positive value. On the calculator, we got a positive value. And that tells us the slope is positive. And that makes sense. The slope is positive here. And then we took an x value after 9.69, any x value here. You could have taken any value. I took an x value of 20. I put that in the derivative, and that produced for me a negative value. And what that tells me is over here, we have a negative slope, negative slope. So we can see positive slope, and here, 0 slope. Okay, we arrive here at the minimum point. At the minimum, once again, at 31.2, x is 31.2, put that in the derivative 0 because there's no slope at that point. The tangent line would be horizontal. But after that point, if we take any x value beyond that, let's say x equals 35, I put that in the derivative. It gives me a positive value, telling me there's a positive slope over here, and that matches what we see on the graph. So key points. Finding max or min points is what this lesson is also all about. Let's keep going. So we're going to talk about optimization. Optimization is the action of making the best or most effective use of a situation or resource. So most effective use. For example, in our situations, if we can find a maximum or minimum point for any function, we can say that's an optimal solution. It's either the least of something or the most of something, which is what optimization is all about, being efficient. For example, let's say we had a curve that represents average costs for some firm or company. Okay, so you can see average costs go down to here and then they rise up again. So what would be the optimal solution for this company? What would be the optimal output for them to produce in order to have optimal costs? Well, the optimal thing for most companies is to reduce their costs. So this could be considered here the optimal solution. In this case, the optimal output leads to the minimum cost. Therefore, this is the optimal output. Okay, so let's get into that. Let's do some problems that have to deal with optimal solutions. Let's say we have a rectangular plot of farmland which is enclosed by 180 meters of fencing. So let's say this fence here is 180 meters long in total, and it's only on 3 sides because the 4th side here it says is bordered by a stone wall, so we only need to build the fence here. Find the dimensions of the plot that enclose the maximum area. Find the maximum area. So notice we are trying to maximize the area here. Our constraint is how much fence we have, but we want to find out the maximum area. So you can do different lengths of fence, and one of those rectangles you create, only one of the infinite rectangles will have the maximum area. So let's begin. Create an area model in terms of W. Okay, what would be the area model here? Okay, the area of a rectangle is simply length times width. Okay, but that is not a function in terms of W. This is a function for area in terms of L and W. So we want to basically reduce this so it only has W on this side as a variable. So let's use some other information we know. We know that the entire fence is 180 meters long. So what can you say 180 equals what? Thinking about these things here. All right, 180 equals 2W plus L because that entire length is 180. So now this allows us to change this area model. Over here in the area model, it says we want it in terms of W. So we want this L to disappear. So why don't we replace the L with L from here? Okay, so let's solve this for L. What happens when you solve this for L? Well, when you solve this side for L, you will get L equals 180 minus 2W. Okay, so that means that we can take that L value and put it in here. And this is what typically happens in optimization problems. So let me point it out. You will be able to create two equations, one here, and then your goal is to take, if it says find the maximum or minimum here, so the one that you're trying to optimize, which in this case is area, is the one where you have to take the other equation and substitute it in to make this two variable equation. So here again we have L. Now we're going to substitute that in for this L here, and we have this. Simplify that further and we have this area equation. Notice now that this area model has only W on this side. So we've created an area model in terms of W. Again, that is one of our main goals when we create when we solve optimization problems, is to be able to do that. Take two equations, combine them into one, and the one that you have here is the one you're going to optimize to find a max or min. Okay, so let's keep going. Let's use our knowledge of quadratics, because we did that. We did power models in a recent unit. And we know when we have quadratics, we can find a max or min point. So here's our area model, and notice it is quadratic. We have a square here, and there's a negative value here also. That means it will be a concave down or a parabola that looks like this. And if somebody said, well, where's the max or min? Well, we're trying to maximize area. So here's A, because it's like our Y value, so it's on this axis. And here's W, so W goes here. So we can see area is maximized right here. That point has a name. It's the vertex, right? Can we find the vertex? How do we find the vertex? Well, we can grab our calculator and find that vertex. Let's try it now. Entered that quadratic into the calculator here. I'm going to graph it. We're going to see it appear here soon. Or maybe not, because the window's not right. So we might have to reset our window. Let's try that. We can, it's hard to say what the window's going to be. But I know I need X values. I only need to see from 0, and maybe I'll go a little bit higher, 20 here. And then for Y values, well, the area is going to end up being something big. So I want a big Y value. Let's just start with, I don't know, 200 and see what happens. Okay, graphing that. There, I can see it. Oh, there it is. Okay, so I need more than 200. So window, I'm going to adjust it some more. Oh, it's still going. Okay, window, I'm going to need to go much higher, I think. So I'm just going to put 1,000 in here and see what happens. So big Y value for maximum. There we go, that's better. Oh, not quite there yet. Interesting, I'm surprised. Let's go. And this is often how it goes with these. You might have to change the window several times before you get the one you want. So I'm going to put 2,000 in there. Why not go really big? All right, graph. Interesting, there it is. Wow, it's still not right. Let's keep adjusting. Okay, I really had to adjust this window a bunch of times, but eventually I think I made a X max of 5,000 and X max of 80 or something and a Y max of 5,000 or something, and it looks okay. I can see the max. Now we do second calc, and we can find the maximum number 4 and set a left bound, set a right bound, right of the maximum point, and then guess. Anyway, you know this process, I think, but we're looking at one more time. Guess that point. Okay, it gives us the maximum value. So x equals 44 or 45, and then area 4050. So that's our vertex. Our vertex represents at a width of 45, we had a maximum area of 4050. So that's using quadratics. We've looked at that before. But now we have a new lens from which to look at max and min points, and is a lens of calculus. So let's look at this one in terms of calculus. So here's our area model. And again, what do we know is true at any max or min point? Well, we know at any max or min point the tangent line is horizontal, therefore there is no slope. So we're going to find the derivative of this right here. So the derivative of this function is this, and now we're going to set that equal to 0, because we're saying when is the slope 0, and derivative represents slope. So the slope becomes 0, and we solve this. What do you get when you solve this? Well, solving it like that, we get an answer of 45. Guess what? It's the same answer we had when we found the vertex. We have found the point, the vertex, the maximum point, and therefore we can go from there and just verify that that's the maximum point. And if you may remember, we had this process. We take the 40, a value less than this maximum point, and we put it into derivative. And when you do that, it gives you a positive value. Now take a value beyond 45, let's say 50. Put it in the derivative and see what you get. What happens when you put 50 in here? Okay, you get a negative value. So that tells you the graph has a positive slope before 45 and a negative slope after. Therefore, increasing, decreasing, this must be a maximum point. We've confirmed. Great. Therefore, we know when W equals 45, the area is maximized. Really important points here. I know this looks kind of simple, but maybe pause and just soak up this main idea here, key idea in our application of calculus. Okay, so now let's go back to our friendly hedgehog, and I have a problem here for you. Please read the problem, and without any guidance, let's give it a try. Let's see if you can find the maximum area of this enclosure. And now let's check our work. There's the enclosure width and length. This time the perimeter is the full distance around a full rectangle, 2 W's plus 2 L's. Okay, but we're trying to maximize area. So area is this, and we're trying to maximize this one. Therefore, this model has to be written in terms of only one variable on this side here. Okay, so using your perimeter one, we can substitute in here. And we know the perimeter is 20 meters. So we replace perimeter 20. We solve this for either W or L. It's your choice. I decided to solve for L, and I got this. And then that L value now goes back into the area model so that we end up with an equation that, again, has only one variable here. Multiply that through a little bit, we get this. It's a quadratic again. This time, rather than using vertex of a quadratic, we'll just jump right to our calculus skills, and we will take a derivative of that and set the derivative equal to 0, because that will give us where our max or min points are. So there's the derivative. Setting that equal to 0, we solve for W, and we get W equals 5. So we just found out when this is 5, that we have found a max or min point. Let's confirm if it's max or min. I'm taking a value less than 5, putting in the derivative, and I got a positive answer. Now take a value greater than 5, let's say 6, put it in the derivative, negative. So that means before the point 5, the graph is increasing and then decreasing. So that means the area must be maximum at 5. All right, so at W equals 5, the area is maximum because it's increasing and then decreasing after. So we have found the maximum area. Well, we found the dimensions that give maximum area. So what is the maximum area? First, let's find L. So L equals 5, because I took that W equals 5, put it back in here, and I found out that L is 5. Well, that's interesting. We have actually created a square. It's 5 by 5. So to maximize the area of rectangle, we actually make it into a square. And therefore, our area is this. Put that back in our area model, and we got 25 meters squared. Good problem. Again, pause and maybe take a close look at everything here. We're going to finish with one tougher problem. So let's go to 3 dimensions. Let's say we have a can of dog food which contains 500 cubic centimeters of food. So here's the can of dog food, and of course every label on any good can of dog food has my dog on it. There's my dog, beautiful dog. Okay, the manufacturer wants to receive maximum profits by making sure the surface area of the can has optimal dimensions. And what that would mean in this case is they want to minimize the can surface, because that will minimize their costs. So we want to minimize surface area. And we are going to use the formulas for cylinder. We did this also in a recent unit, so take a look. Volume of a cylinder is pi r squared times h. Base area, circle, times h. And the surface area is 2 pi r squared plus 2 pi r h. 2 circles, top and bottom, plus the lateral area, which is this. Let's use those formulas to set this up. I'll get you started and you can try. So first of all, we're going to say the volume equals this. And we know the volume is 500, so we replace that here. Okay, that's the volume formula, but that's not the one we're trying to optimize. The one we're trying to optimize is actually the surface area, because we want to minimize the surface area of this can. So here's our surface area formula, but notice we have an R here and an H here. So again, our goal is always to eliminate one variable so that we can have an equation of A equals something with only one variable, because then we can take a derivative. So which are you going to replace, R or H? Which is easier, do you think? Well, we can see clearly H will be easier because we only have to replace it once. So let's solve this for H. That solved for H is 500 over pi r squared. Now that goes into our area model here, replaces the H right here. Now simplify this, what do you get? Okay, here's the equation we get when we simplify this, because the 2 times 500 is 1,000. The pi and the r cancel pi and r here, but there's one r remaining in the denominator. Okay, of course we can graph this and find a minimum point, but let's use calculus. So here is the area model we created, bringing the r up to get this. Now take the derivative. Check your work. Now set the derivative equals 0. Now solve for r. You can graph this to solve for r and find the 0. There's the value for r. Now we're going to double check that that's the minimum. check a value before and check a value after and see, oh, negative, positive, therefore this is a minimum. Great, now here's the graph, we can see it's a minimum, and here's the graph with the derivative, and you can see the